Well, thank you all so much for being here in this beautiful day. It is my pleasure to introduce you to Matias Castro-Tapia. We met when we were both undergrads in Chile. He did his undergrad in the Universidad Católica de Chile. And then he moved to Montreal in Canada to do his master's at McGill University. And now he's a PhD student there, working with Andrew Cumming, also with Rafa Fuentes, Maria Conchasa, present here today. He's an expert in stellar evolution, has a lot of experience in stellar evolution, and today he's going to be telling us about his cool work on white dwarfs. So please take it away.
Thank you. Okay, so thank you, Connie, for the introduction. As you mentioned, I'm Matias. I'm a PhD student at McGill. I'm going to present about the work that I have been doing as a grad student at McGill. The title is Cool White Dwarfs, Crystallization, Convection, and Magnetic Field. So I will start from the very basics. So how we form a white dwarf? We form a white dwarf going through the whole stellar evolution. So it's the final stage of many stars that are similar to the sun. We say that these stars are in the main sequence, for example, the sun, which are characterized for hydrogen core burning. So they're burning hydrogen, producing some helium. This process lasts for billions of years until they exhaust their hydrogen in their core, and they start burning hydrogen in shells, in outer layers above the core. And they also expand due to that. They form a red giant, which is still with about the same mass, but 100 times larger than it was before. In this red giant phase, we have even more nucleosynthesis processes. At some point of the red giant phase, we have helium core burning, then helium in shells as we have before with the hydrogen. We have a lot of mass loss. The timescales in this stage are very quick. So I would say that the processes are very violent. And for more massive, even more massive stars, we can even drive carbon burning. And after all this burning, at some point we don't met the conditions to drive more nucleosynthesis. So the star will construct very quickly and will form a white dwarf star, which is a very small star, a very compact object. In this case, we still have about around of order of solar masses, but all this mass is contained in a radius of the size of the Earth. So it's basically a very compact object due to the very large density. Okay, so these objects don't have more burning, they only cool over time, but also they are sustained to not collapse due to the gravity, due to the electron degeneracy pressure. So basically we have quantum effects there to consider for the electrons that change the whole equation of the state of the star. They don't collapse basically due to this pressure. Most of white dwarfs are formed with carbon-oxygen cores due to very nucleosynthesis processes that I'm not going to explain here. But for more massive white dwarfs, we can even expect oxygen neon cores. So why to study white dwarfs? Most of the stars in our galaxy will become a white dwarf as the final stage of their evolution. More than 90% of the stars in the galaxy, they become cooler over time in billions of years. So they are good to measure ages of stellar populations. You can imagine that modeling a cooling process only is much more easier than it's much easier, sorry, than modeling other stages where we have different nuclear burning processes and also the cooling happening in the surface. So they are good to measure ages of stellar populations. And since Gaia DR2 and DR3, the number of white dwarfs identified in the galaxy have increased by a lot. This is why Gaia allows us to measure the parallaxes, and we can identify the distances and obtain a good measure for the magnitudes and the luminosities of these objects, so we can trace them in the color magnitude diagram, basically. So pre-Gaia, we only have a few white dwarfs, most of them from stellar clusters, because we can measure distances there, and we can identify the different stellar evolution stages from a cluster which is basically the same distance. But after Gaia, we were able to identify many, many white dwarfs. So now people can test theories about evolution, the evolution of white dwarfs, since we have a lot of data. So as I mentioned, sorry. Okay, it says more data offers the opportunity to test more theories. One interesting theory is that the high density plasma in the white dwarf interior can experience a first order transition. It means a crystallization. It means that this plasma is very dense, and as it cools over time, the ions inside will rearrange in a solid lattice. So how this is and this theory is important, and it comes from the 60s even, and it's important because phase transitions offer an extra energy source for the white dwarf cooling. Here, for example, in this dot, we have luminosity beams here for the Gaia data, and this is just the luminosity density over these beam points. So basically, when we have only the cooling model, the simple cooling model, we cannot match this luminosity density distribution. But if we have the phase transition, meaning crystallization, we will have a energy related to this phase transition, and also a gravitational energy due to the distribution of the solid part and the liquid in the white dwarf. And we can see that theoretical models adding this extra source can explain better the data. Here are some points that are not fit. There's some other interesting theories related to that, but it's not going to be the focus of my talk. The other interesting problem that I'm going to, which is basically the work that I have been doing, is that the multi-component plasma crystallization can generate buoyant instability and potentially power a dynamo to generate a magnetic field. This buoyant instability is created, I'm going to explain more details later, is created because the solid phase and the liquid phase in the transition have not the same composition. So they are buoyantly unstable, produce convective motion, and people say that this combined with rotation can generate a magnetic field. How this is supported by observation here in this figure, for example, we have different white dwarfs. Some of them are magnetic, which are the field side circles. Here we have the cooling age, the masses, and we see that most of the more magnetic white dwarfs appears after these lines here, which predicts the onset of crystallization. So this idea have gained a lot of power, basically, because the observations are indicating that magnetic white dwarfs are very cool and cool enough to form a crystal lattice. So, but this dynamo generated by convective motions basically depends mostly on the convective velocity predicted for the convection, which scales proportionally to the magnetic field strength. So we need a consistent calculation for this convective velocity. So as a quick review of these theories, of this theory, in the paper that first introduced this crystallization-driven dynamo, they use energy scalings for obtaining the convective velocity. So basically, they say that the gravitational energy driven by the redistribution of the elements can power the dynamo. And similar works using rotation have similar scaling, but including rotation have found even larger velocities or similar results. However, we will see that in white dwarfs, the thermal diffusion is very important. So other works where people have been trying to compute this velocities, they include the effect of thermal diffusion, and they found a very small velocity, even about 3 orders of magnitude smaller. However, these works, as you see, are from the 80s and the 90s, so and are based on all analytical models which have not been reproduced again. And some of you have could ask the question, why don't compute the convective velocity from stellar evolution codes, which handle convection usually, but in this case, modern stellar evolution codes don't handle this very discontinuous transition in the composition. So they just assume instantaneous mixing upon crystallization, which avoid computing the convective properties. So we need a whole new theory basically to find an agreement about the convective velocity, which is important for the magnetic field, as I mentioned. So the outline of our work is the following. So as a big picture, we have a white dwarf cooling over time. At some point, it starts crystallizing, the element redistribute, generating an instability, driving convection. So we develop a new consistent mixed length theory that could be applied to white dwarf crystallization. And we show even that could be applied to every other stellar evolution case. And then we estimated the convective velocity for this case using modern cooling models. We test basically our theory using this very popular stellar evolution code, which is being developed over the years, and even the last release was a few months ago. Then, having the convective velocity, we will use scalings that relate the convective velocity with rotating magnetized flows, which are the case of the interior of the white dwarf, to calculate the strength of the magnetic field. And after that, we will evolve the magnetic field to get a value of the surface magnetic field, which is a value that we can compare directly with the observation, which are, as you may know, observations of surface magnetic fields. Lastly, we will propose some improvements to our calculation and current white dwarf models, mostly exploring different compositions in white dwarfs. We propose a way to implement a 3-species phase separation in MESA. Most of the stellar evolution codes right now have only a 2-species phase separation, which covers more than 90% of the white dwarf interior composition. But we have some elements that could be important here, and we also explore the case of oxygen-neon white dwarfs. So how crystallization works? So multi-component plasma show a redistribution of the chemical elements in the solid and liquid. Imagine, for example, that you have a fluid that only has one component. If you freeze this component, probably you will not see any redistribution of the elements, because in the whole fluid you have the same composition. But if you have a mixture of composition, the transition shows changes in the composition between the solid and liquid. So we characterize this crystallization using this plasma coupling parameter, which basically measures the Coulomb energy over the thermal energy. And we have here the temperature, and here we have this separation that depends on the density. So it will also depend on the composition. And for white dwarf stars, this is like the critical value to start crystallizing, and this is a range of values because due to the composition's variability, this value is different, as I mentioned. So we can also characterize this with a limiting temperature, which is basically the temperature where we transit from solid to liquid. We use this phase diagram usually to characterize this. For a 2-component plasma, we can characterize with one of the abundances, in this case oxygen, and here the temperature over the melting temperature. And in this phase diagram, what we are showing in this part, for this space, for this parameter space, we find the plasma in this liquid phase, but if we transit here, we find it in the solid. We have these two lines. This is called the liquid line, which shows the maximum value at which we are liquid, and this is the solid line, which shows the transition to the solid. However, we have this unstable region, which at constant temperature, the plasma cannot exist in this, basically in this region. I'm not going to explain why, because these phase diagrams are based on free energy minimization calculations, and some people have done like molecular dynamics to construct these diagrams in a more accurate way. But the main takeout of this is that at a given temperature, the liquid and solid have different chemical abundances. For example, imagine that we start with a boiler at certain temperature here, at certain composition in the liquid. The composition starts being constant, but we reach this line as we cool. So we cannot exist in this part, so we have to move to here to transit to the solid. So a solid will be more enriched in oxygen than the liquid part. And a similar diagram is found, for example, for oxygen-neon mixtures. This one is for carbon-oxygen. So again, what is predicted from the diagram? That the heavier elements are encased in the solid phase. When we form the crystal will sink and settle into the core. So we will have a solid phase which is enriched in oxygen. But to conserve mass, basically to form the crystal, we have to put more oxygen here. And we have to leave behind a region which is now carbon enriched and pure in oxygen, right? And this new layer here will be convectively unstable with the initial composition, because this now, the mean molecular weight here, if you want to see it that way, will be much smaller than this part here. So basically, this part will be heavy and this part will be light. Oh, sorry. And in this example from a cooling model from MESA using the two species phase separation, we see as the solid advances from the core, the solid part towards the interior is enriched in oxygen in the midline, and the outer layers are enriched in carbon, which is the prediction from the phase diagram. So how convection works now? So as I mentioned, we have a fluid where we have a zone which is heavy compared to another zone here in the bottom, which is lighter than the other one. We have the gravity in this direction. So what will happen? The fluid which is lighter will start to rise due to this buoyant instability, and the heavy element will start to sink into the light element until we reach a mixed region which is stable. So mathematically, this works as follows. We have two zones that have a density difference. We usually use the density gradients instead of the local value of the density, which is and for value less than 0, this layer will be unstable to convection. If we have larger or equal to 0, will be stable, which means that the heavy will be in the bottom and the light in the upper side. So we can drive this density contrast in stars by a thermal difference and a composition difference. So we usually use these nabla gradients that define the thermal gradients of the surrounding, the thermal gradient of the fluid elements. We usually, to describe the convection, use this theory that we take a bubble of the fluid which is less dense, and we start this will start to rise. So we have the thermal gradient of the element and the composition gradients of the surroundings. In this case, we assume that the bubble itself doesn't exchange composition as it rises. It only will change composition when it mixes at a mixing length, a characteristic length scale, which is similar to the pressure scale height. So this is why also we use this gradients in terms of the pressure.
Just a very nice question. It's a very dense plasma, right?
Mhm.
So still we are using this, like whatever normal fluid equations we are using. Can any quantum mechanical effect will come into the picture?
Yeah, actually, it will come to the picture, and it's all contained in the equation of state that you use. So basically, the equation of state for a white dwarf will be different if you have, for example, an ideal gas. And this is basically the way you relate, for example, the pressure to the other quantities, as the temperature, the composition. So basically, it's all the information contained inside this derivative. It's just the thermodynamic definition of this.
The Ki coefficients, they account for the generic effects.
Yeah.
For idea of that, those are one or minus. Yeah. So it's all equation of state, we just encapsulate in one power.
Yeah. Okay. So now, the important question, the convective velocity. How we determine the convective velocity from the density contrast? This is a very common scaling for the buoyant acceleration, which directly relates the convective velocity, and is a function of the gradients that I mentioned before, right? So how we usually evaluate these gradients? Wait, I'm gonna move. Oh. Yeah, no, it's okay. So we usually evaluate these gradients. Some models use this simplified version of the gradients. One of these describes the total heat flux in the white dwarf, or some of them even could evaluate the direct temperature gradient in the temperature profile. But this is the most simplified version of this. And for the element gradient, some people assume that the element moves adiabatically as it rises, because we are describing the light element moving into the heavy region. And this leads to a classical criterion, which is known as the Ledoux criterion for convection. And you may know that if we drop this composition term, we end up with a Schwarzschild criterion, which is only thermal convection. But in this case, we have this composition part. So as I said, if we assume that the convective motion is adiabatic, we can easily evaluate this convective velocity. However, and here is a huge problem, thermal conduction means diffusion from the electrons in the white dwarf keep the thermal gradient mostly stable, which means two things. One, that the convection in the interior can only be driven by the composition gradient, and that the fluid elements, the bubbles that we consider, lose energy by radiation as they move. So the picture is now a bit different. We have a composition difference here. In this case, this is carbon, so it's lighter. If you assume carbon in mixture, now the bubbles will rise due to the convective instability, but they will emit some energy, and they will be deaccelerated by this. So we have to define a new quantity, which is the convective efficiency. Don't get confused with the coupling parameter, it's totally different. This is a dimensionless parameter, which basically measure, we can think about it like as the thermal time for the transport of heat divided by the convective turnover time, or the transport by convection divided by the transport by thermal diffusion. So it's related to the thermal gradients because it measures also how the bubble is adjusting to the background thermal gradient as it rises, meaning losing energy. So now we cannot assume anything about these gradients, and the convective velocity will be different. And if we have a fixed mixing length and a fixed thermal diffusion locally, we can measure the convective velocity from this. So what we have so far, convective efficiency, a relation for the convective velocity that is also depending on the gradients, but we need to solve the gradients, basically. And for that, we use the fluxes from the stellar models. we use the composition fluxes for each element. Here we write the composition flux, which is directly related to each composition gradient, but accounting for the summation of all the elements. So basically, we take the mixture, we can write a term for the composition gradient, considering the whole mixture. And in the more simplified case, we have two components for white dwarfs, carbon and oxygen, so we only need one variable. And we also have the heat fluxes, the radiative flux, the convective flux, which are related to the thermal gradients. In this way, here we again have this quantity, which basically represents the whole flux if we have these quantities that are local quantities in the model. And we end up with an equation, a 5-degree equation, actually, for the convective efficiency, which is basically the convective velocity in some way. So we can extract, for example, the composition flux from mass conservation, following how the composition of each element change over time, and also from energy conservation, looking at the luminosity at each layer that we are evaluating the convection, we can obtain the total heat flux. So now we have something that depends on the composition flux and the heat flux, which is directly proportional to the convective velocity. So we now don't evaluate the gradients, but solve for this in terms of the fluxes. And we also get solution for the gradients in terms of gamma, and now they are different from what we saw before for the monorail. However, we face another problem again. Previous works have found a different equation when including thermal diffusion in convection, which is this one, a good-looking equation, a 3rd-degree equation. And this equation is currently used in MESA, and to include composition gradients, they use a correction for this adiabatic gradient. Another similar works have found a similar equation, but in other contexts. So then, why doesn't mine look like this? So we did a kind of a review of the literature on how people define the convective heat flux, and we have found an inconsistency. They usually define, and I'm gonna say that in all the papers that I found this, they don't justify why they define this like this. So basically, they use the enthalpy to define the heat. Basically, they say this is equal to the heat transported is equal to the difference in the enthalpy, which leads to this expression, which is directly proportional to the density contrast. But the energy, the heat transported is basically not the same as the density contrast. So using the formal definition of heat, so temperature times the difference in the entropy, we find out a different expression, which also has this composition term, but which is different from the another one. And we found out that we can even banish this term for the white dwarf case. So as I mentioned, this equality is only valid, I mean, these two values are only valid when we have certain conditions. For example, composition gradient equal to 0. So maybe people have looked at very old theories of thermal convection, which was first developed, and they say, okay, we will extrapolate this and somehow to get a similar expression for the heat. But we have to obey the laws of thermodynamics, use the formal definition of the heat. So we compare both definitions using our equations and getting the gradients and using the relevant thermodynamics quantities from a white dwarf cooling model from MESA, and we get this. So basically, the heat flux defined by the enthalpy is quite different to what is defined with this term. And we see here that this term has a small contribution to the heat. So we only use these thermal gradients to define the heat flux. I forgot to mention here, but in the case of neutron stars, accreting neutron stars, they have found a similar relation for the convective heat flux. And this implies that the convective heat flux, goes inwards instead of outwards. And this is supported by numerical simulations. This is a work that we did with Rafa. Rafa ran some numerical simulations where an outward-like element flux unstable to convection will reduce into an inward convective heat flux. And just to mention that in this paper, we also explored this extension of the mixing length theory, but for a very specific condition. We assume that the heat flux, basically, the total heat flux is zero between the radiation and convection. But yes, this makes sense because in a thermally stratified medium, we expect that if we don't have any instability driven by thermal gradients, we only will steep the gradient that we have at the beginning. So to answer the question about how vigorous is convection, we have our bad-looking equation, but we can evaluate it. We can solve it for only the positive solutions of this polynomial, real and positive, which will indicate that we have a consistent solution for the convective velocity. And you read that. We have one only consistent solution for different values of the space parameter of the composition flux and the heat flux. We find out that we can describe the classical convection theories driven by thermal gradients here with this theory. And we also include the bar now in this whole equation driven by composition. Those two are very efficient. We have a gamma value and efficiency larger than 1, but we have this inefficient regime, which we found that is consistent with thermohaline mixing. So if you look into the literature for thermohaline mixing, they also assume directly that the total heat transported by thermohaline is 0. And it's true, it's very small, but it's not exactly 0. So we can describe the same mixing theory from overturning convection to thermohaline through this equation. And now, for the case of white dwarfs, the important part. We follow the crystallization of the core in different cooling models in MESA to set up the composition flux. So we follow, this is the mass of the core, basically the rate of change of the mass of the core, the radius of the core, and this composition contrast comes directly from the difference found in the phase diagram. As we saw before, it depends on the composition and in the temperature at which we are. We evaluated this in the model. We obtained the following. Here we have models for 2 different masses. We start with very efficient convection driven by composition, but then thermal diffusion acts to reduce the velocity, and we fall into this thermohaline regime of convection. Why the convection is so efficient at the beginning? We see in this quantity that for a very small core, we will have something that goes closely to 0, which goes basically to infinity. So when we have a very small core, the flux is huge, and we can drive convection very efficient. But then, as the core grows, the thermal diffusion is more efficient and reduce the velocity by a lot. So if you remember, okay, so the conclusion first is convection happens in 2 regimes in crystallizing white dwarfs. It's strongly dependent on the composition flux, and we found a transition at this tau value equals than 1. So it's the important value to evaluate. If we are larger than 1, we are efficient. Less than 1, we are inefficient. So in the previous work, if you remember, some of the works found this range of velocities, and the other ones go through the very small velocities. So they were both correct, but they occur at different times in the crystallization. So how vigorous is convection? We measured the tau value, which is the important parameter, and we found that tau is larger than 1 only for about 10 megayears, which is 10 million years, a lot of time, but not a lot of time compared with the scalings I mean, compared with the time scale of the evolution of white dwarf, which are billions of years. So, and when I say enough for generating a strong magnetic field, which is our main focus. Yay. So now, before jumping into the scalings that we found for the magnetic field strength, we have to understand a bit more about this crystallization-driven dynamo theory. It's similar to what is predicted by to the Earth's core, which is basically said that the Earth can maintain its own magnetic field by having convection here in the outer core and having a solid core here. So convection motions are combined with rotation, which rearranges the fluid motion and shape the magnetic field. So we need rotation to power the dynamo as well, basically because of the shape of the magnetic field. And this is supported by, for example, observation. Here we only have rotating stars. So these ones that are close to zero are not actually close to zero. They just have short periods. And those that have about the shorter periods are, most of them are magnetic vectors. So observationally, rotation seems to play a role for the magnetic field generation. So to answer the question, what is the magnetic field strength? Classic scalings use the equipartition, basically said that the kinetic energy driven by the convection, proportional to the convective velocity, is mainly equal to the magnetic force. The magnetic energy. So basically, we power with the total energy of the total kinetic energy of the convection, the magnetic field. However, as I mentioned, we need rotation, and the strong magnetic field observed suggests that the magnetic force also balances the fluid. So we use this other balance that includes a balance between three forces: the magnetic force, the buoyancy itself, and the Coriolis force, which is shaping the fluid as I showed before. In this work with Rafa, we did that. We can see here that in the equations that the magnetic field and also the convective velocity now are limited by the gravity and also the density contrast, which is basically the convective instability. And as we mentioned before, the convective instability is driven by composition flux, which diverges for a very small core. And in this region, we are at almost constant density. But the gravity is very small, because in the region where we have the convection, we have the very small core, and above that we have a very thin layer of liquid, which fills the gravity of this small core. And this scales with the radius of the core and goes to zero. So basically, what this said, that the dynamo-generated magnetic field has an upper limit. Both contributions cancel each other, and we can only generate a magnetic field with an upper limit. So now we computed the magnetic field strength for different times of the cooling. So here we see, now we have the magnetic field strength here, but we now see the magnetic field generated for different regions of convection. Here is the efficient convection, only about 10 megayears, but then we decay into a very inefficient convection, which can only generate weak fields. So we take this maximum value of the magnetic field, and bam, we put it to compare with the direct observations. So we see, even when not much in the data, because there is a lot of scatter in the actual strength of the magnetic field measured, we see that it's about of order of magnitude of the magnetic field observed. But we have to consider something else here. We cannot just take this prediction for the magnetic field and compare with observations. We are missing something very important here, which is sorry. How the field evolves before emerging. For the efficient regime of convection, we have the convection is embedded to the very inside of the wave. So here, we actually don't know exactly what is the extent of this convection, but using the prediction from the mixing done by Mesa with two different criteria, we find that during the efficient regime, which lasts until like here, approximately, we have convection in a very small zone, not small, but not reaching the surface. So we need to transport the magnetic field out. We use now this transport equation, basically the induction equation for the magnetic field. We take the diffusion part and we compute the magnetic field evolving over time. So we take two contributions for the diffusion of the magnetic field, the electrical conductivities, sorry, the ohmic diffusivity that comes from the electrical conductivities, and a term which describes the turbulent transport of the magnetic field, because we still have convection, which is, even when it's inefficient after forming the magnetic field, it can also transport the magnetic field out. So we evolve the field. Here we show an example evolution of the field evolution. Here we take, in this side, we take the radius coordinate of the white dwarf model. Here we have the magnetic field average over all the angles. So this value here is the magnetic field average as a function of the radius, internal radius. And the initial condition that we take for simplicity was that the magnetic field is constant with the radius embedded to the initial convection zone. And also we take the convection zone as a free parameter, so we run different models for different convection zones. But the main conclusion of this is that when reaching the surface, the magnetic field average over all the angles is highly reduced from the value that we had at the beginning. And this also happens because of the evolution of the diffusivity. We have assumed a spherically symmetric diffusivity, and the diffusivity decreases as the solid core grows. It means that when we form the solid, it is harder to transport the magnetic field. We have a very strong conductivity there. And here we have an example of the 2D projection of the magnetic field lines, which basically show the same result, that the magnetic field evolves, reach a certain value on the surface, and then due to the crystallization, we cannot transport the magnetic field further, but yeah, we end up with a reduced value of the magnetic field. So now we are in the position to compare with observations. Why observations are from surface magnetic field measurements. Here, we take the prediction of the field in the surface from our transport model for different times compared to ages observed in magnetized white dwarfs that are crystallizing. In these shaded areas, for example, here, the free parameters that we use, the turbulent diffusion, the outer convection zone at the beginning. But here, this shaded zone covers a range of average cooling ages observed in white dwarfs, because at different ages, we observe different surface values according to our models. And in this dotted line, we have our first prediction that was very good at the beginning, but now is reduced by the transport of the magnetic field. Those blue points are magnetized white dwarfs. White dwarfs are expected to be crystallizing, so are the white dwarfs that we should be comparing with. And our conclusion is, in the best case, the crystallization-driven dynamo theory can only explain magnetic fields that are a few megagauss in carbon-oxygen white dwarfs, at least. So this theory cannot explain the whole range of magnetic white dwarfs, even when they have started crystallizing. So we have more work to do to figure out this problem. We have only considered in all the models that I show you carbon-oxygen mixture for white dwarfs, But more massive white dwarfs usually go through more burning processes, which leads to a more varied mixture. The compositions are, for example, we have carbonoxy neon, carbonoxy magnesium, oxygen neon, but also with sodium and magnesium. So we need more complex phase diagram. These diagrams now have 3 different components. We have the same as before, we have a liquid region. This is the coupling parameter, so it indicates the temperature. This one is higher temperature, lower temperature, because it's inverse scaling there. So we start in the liquid zone. Imagine that we start here with a waiver with this composition. Here the lines indicates the triangle lines indicates the composition as we are. This phase diagram moves as we are cooling. We will reach this line eventually, and we will have to transit to the solid phase again, but we have again this difference in composition, but now for 3 different elements. And these diagrams, we have the technology to do these diagrams. It has been done for several people over the years, but they haven't been applied to any stellar evolution code. So we are proposing a way to implement these diagrams in MESA, for example. We see here the evolution of 1.1 solar masses white dwarf, which is mostly oxygen neon in its core. This is the current implementation that is in MESA that only includes these 2 elements, which are the most abundant in the mixture. But we propose, apart from the 3 species phase separation, add another isotope to the mixture. So here people have ignored that even when we have neon, they only consider neon 20 and not the isotope neon 22, which has a small value here, but can also be added to the mixture. And in the uppermost panel, we see with 3 species. We have oxygen, neon with both isotopes, and sodium, which is the 3rd most abundant in this white dwarf model. So what we observe, first of all, as I mentioned, no public white dwarf model with this implementation. And we observe that the composition and mixing significantly change for different stages of crystallization. Here, in these shaded areas, we show the advance of the solid core. If we look at the 90% of the solid core, they look different from if we have all the 2 species phase separation. And if we look here, this is the liquid zone for 50% of the core crystallized. And in the liquid zone, we experience mixing. But here, the mixing region seems to be extended until here. But here in the other 2 cases, we see a more extended mixing zone. So if you remember, what was the most important parameter in convection driven by composition was this tau parameter. If we have a tau parameter larger than 1, we have efficient convection. If we have a tau parameter less than 1, inefficient convection. So the effect of adding the 3 species phase diagram can change the fluid dynamics, obviously. The efficient convection will be longer in time. If we see here the log scale, in this panel, for example, we have values of tau larger than 1 in the blue line with the 3 components crystallization for about 2 orders of magnitude larger in time for the green line, which is the current implementation in MESA. So we have efficient convection for more time. And we see the isotopes that are neutron-rich, meaning that in this case, we refer neutron-rich to larger than 1/2 the atomic number over the mass number, have a greater impact. Here, we have oxygen, neon, sodium. These 2, neon 22 and sodium 23, are neutron-rich, and they have a huge effect. But here we have magnesium and neon, and we see that the only inclusion of the neon 22 into the phase separation can even compare the fluid properties for the convection to include the magnesium 24, which is not neutron-rich, considering that that definition of neutron-rich. So this is work in preparation. As a summary, we have developed a mixed length theory that can be applied to improve current white dwarf models. We found two regimes of convection, which connects basically the whole theories before about the convective velocity estimations. We have made the most detailed analysis of the crystallization-driven dynamo theory to the date, with the main conclusion that we can only explain a few megagauss magnetic white dwarfs in the carbon accident case, given the condition at which it's generated. And we also propose a new implementation of the three species phase separation in the stellar evolution code, which can potentially be used for more detailed analysis in massive white dwarfs. Future direction, we still need to implement this new MLT directly in an evolution code. We have to analyze the different information channels of the ultramassive white dwarfs, because different information channel leads to different composition, different time for the crystallization, etc. We are already working on this with another student at McGill and my supervisor Andrew Cumming. And we also have to look at alternative solution for the magnetic field in white dwarfs. For example, a fossil field generation, a fossil field origin, which means that the magnetic field have survived previous stages of the stellar evolution and then emerge in the white dwarf phase. We are working with this with Maria and with another student at McGill. We need much more work and collaboration to complete the puzzle of magnetic white dwarfs. Thank you. So, questions?
So you mentioned that this crystallization-driven dynamo is very similar to what powers the geodynamo. So we live in times where we are looking for many exoplanets right now, and some of them are called lava planets or martian planets, where they cool down over time and they solidify. So is it possible that in these new exoplanets that we're discovering now, you could have a similar effect, like a crystallization-driven dynamo?
I would say that it will depend on the conditions of the crystallization, because in lava planets, what happens that the Prandtl number is very high compared to the Prandtl number in weather stars, meaning that the viscosity is much more important in lava planets. So when we form, we drive a phase transition in planets. Wait, I'm gonna show something. I don't have a slide for that, but I'm gonna explain it very quickly. When we have that transition in planets, the conditions inside the lava planets meet in a way that we can exist in this unstable region. So basically we have a mixture of solid and liquid that doesn't separate as it happens in white dwarfs. So the conditions are different, so we need to analyze that. More questions? Yes.
I had a burning question that was then answered on the first point of your future directions, because I was going to ask what happens when you put this sort of 5-root MLT beast into Mesa, but it sounds like that hasn't been done yet, right? How is that a heroic effort? Like, is that MLT is kind of fundamental to Mesa, right? So this new compositional MLT that you've got, is it an easy switch in Mesa to switch the one polynomial out for the other, or is that a pretty fundamental change to Mesa?
Actually, that's a great question, because as I mentioned, in Mesa they solved this equation for the convective efficiency, but the equation that I showed before, the third-degree equation, and that equation is pretty simple. It's not pretty simple to solve, but if you put in like your computer, you find an analytic solution for that, so you can directly evaluate that. And the curious thing about Mesa is that this implementation with the convective efficiency theory relies on taking the heat flux into the equation, but when adding the composition gradients in Mesa, the composition gradient is measured directly in the composition profile, which seems to be a very strange way to do it, since we are driving the we have two options. We take the gradients and compute the fluxes, or we take the fluxes and compute the gradients. So we're proposing to do the opposite side. So it requires like a very fundamental effort into the code to implement this MLT. And also related to that, usually in stars, we have convection driven by thermal instabilities, and we have a stable composition gradients, which basically prevents convection. So we are mostly here, and the third-degree equation can handle this, and even this part. But when we enter in this zone where we are compositionally unstable, MESA cannot handle that. And also, people haven't looked at that because this only happens in white dwarfs and also in neutron stars accreting material and crystallizing, but we don't have that model for neutron stars in MESA even. And they treat this thermohaline using an approximation, assuming that the heat flux transported is basically zero. Actually, I have a backup slide for that kind of question. Just wait a second. So what we know about the Ledoux criterion is that we take the adiabatic gradient, and the formal definition of the Ledoux criterion takes the adiabatic gradient for defining the element gradient. But now we have used this criterion, which basically includes the actual gradient of the fluid element. And in one of our papers, we demonstrated that under certain conditions, for gamma very small, we can even resemble the diffusion parameter in all calculations of thermohaline convection. And we also compare that with current implementations of the thermohaline convection, basically computing this diffusion parameter, which is important for the transport in the stellar interior. We compare here with the Kippenham theory and with the theory of the reduced density ratio that I think you have worked on. We see that even assuming different mixing lengths for the thermohaline case, the transport coefficient is pretty similar when taking this theory and the other theories that have been developed now.
This is diffusion of what on the axis?
This is the diffusion parameter for thermohaline.
Of composition or of heat?
For composition. It's basically the convective velocity times the length scale of the mixing. Any more questions?
Very basic question. Like dynamo means we know that it basically converts one type of energy to another type. So in this crystalline-driven dynamo, what kind of energy you are converting to the magnetic energy? Is it the like thermal energy of the star, or is it the rotational energy of the star? I mean shear.
I think, yeah, we only mostly rely on the force balance, but I think at the end we end up finding that the scalings for the energy are pretty similar to the equipartition. I don't remember. I think Rafa remember that because
It's the gravitational potential energy released due to the chemical separation when it's converted into magnetic element. It's like buoyancy because of that fluid motion. Yeah. And second is that what is the like composition of the composition in the sense like component wise? Is it the colloidal dominated or toroidal dominated? Because I think in one of the slides you also discussed the effect of shear.
yeah, usually observations suggest that the magnetic fields in white dwarfs are mostly a dipole, and even could be an offset dipole, which can be explained by also more components in the polar direction, basically taking the dipole plus a quadrupole. And yeah, I think there is no like evidence of a toroidal component in white dwarfs at least. Is that answers your question?
No, I was just trying to understand the cycle. Generally, like in general, like let's say in case of sun, like which is the most explored dynamo theory in our understanding. there's a conversion between the colloidal field and the toroidal field. It's like there's some generation and then again destruction and generation. So is there any cycles going on in this case of dynamo?
You can see the convection zone is the outer part from the sun, but he's talking about a system where it's in the interior, right? So you got a giant shield blocking your view from where the dynamo is being formed.
And there are on-cycling dynamos too,
Okay, yeah.
where you don't get a solar.
That's another measurement. You assume you're measuring one component of the dynamo. So it's a tough measurement.
I think that, yeah, I think that discussion already answers the question.
Sure.
I wanted to ask one question. So you said that your model can only reproduce magnetic fields lower than 4 megavolt?
Mhm.
So which of the things that you're trying now do you think is the one that has the more potential to really fix? Move that really farther away.
Yeah, actually,
Because-
yeah, actually, I don't know. We're working with Maria in this idea that during the main sequence, if you have a convective core, you can try a magnetic field, and this magnetic field, if it survives until the white dwarf phase, it could emerge in a time scale comparable with what is observed, which means that even if we have a fossil field embedded inside the white dwarf, it can appear kind of late, even after the crystallization line. But I think it could be a combination of different processes is what is the most accepted thinking right now. Even for the more massive one, people kind of rely on the idea that they could be formed from mergers of two white dwarfs that are with the summation of their masses doesn't exceed the critical mass for a white dwarf, and due to the shear of the merger process, you can generate a magnetic field as well, powering the dynamo due to this differential rotation in the merger. But I will say that I don't know, but probably it's multiple channels. We have in different astrophysical problems that multiple channels are even the best option to explain different physics. We change a small parameter in our calculations, and we change everything basically. So I would say that multiple channels is the more accurate way to explain that. Maybe we have to analyze case by case the magnetic white dwarfs, but yeah.
Okay, awesome. Let's speak here again.